Thank you, Christian. Good morning, everybody. So let's first thank my colleagues with whom I'm working during this year, and they are responsible with me for most of the work, so we share the responsibility and also the all the bad and good moments. And okay, maybe the title is a little bit pretentious. I will not show really everything about Rockfall, but it is just mainly what we are working on and what we can observe. So the idea is just to talk something about the facial topographic description in Rockfall modeling and analysis, something about the calibration, and something about this has been presented also yesterday in a nice session early in the morning, and something about uncertainty. And as I was saying, as I was mentioning before, I still have a lot of uncertainties about Rockfall modeling. And then I will try to talk something about countermeasure design, or the use of Rockfall modeling for countermeasure design, and the possibility to use results from modeling for hazard and risk assessment. So, okay, we know that rockfalls are usually occurring in quite harsh environments with high cliffs, very high roughness, complicated topography. The sources can be very diffuse on the terrain, so they can be also difficult to find and to map. And these result usually in a very large uncertainty, and in most of the parameters and in most of the evidences of the rockfalls. So we will have also a high variable rockfall frequency and energy, and we will have a very scattered dynamics along the slopes. So this will require complex modeling, and the degree of complexity is changing with time, and we are seeing that there are very big development on that. And this is making also extremely difficult sometimes to correctly position the countermeasure or to evaluate in a reliable way the susceptibility and the hazard. So one of the controlling factors are the source position along the slopes, and because they can control the initial condition along the path, they can control the path, and they can control also the final reaching point by the rockfalls. So at the same time, the definition of the rockfall sources is changing according to the aim of the study and the availability of data and the final result that we want to obtain. So that we can try to define regional or local source areas. We can try to define, or we can assign to the model a specific source area just because we are back analyzing a specific problem, or we can simply find the most dangerous blocks or the most dangerous sector of the cliff. And at the same time, we can also define source areas according to the need for designing or verifying a countermeasure. I will not go through into detail about the methods for mapping and establishing the right source areas, but we know that we can use a bunch of different methods and different surveying techniques. And there is one more point that probably is connected both to method and surveying. It is the definition of the design block size, so the size of the block that we want to model, and that it can be associated to a specific source or to a specific problem that we are looking at. So one of the problems that we commonly have is the description of topography, and usually there is a strong effect played by topography on directing or redirecting rockfall trajectories. And it has been empirically shown, and also yesterday we have seen that there is a dispersion that more or less is 20–30% of the length of the slope according to field observation. And at the same time, we have the topographic modeling is controlling the slope geometry, the roughness, the the interaction between block geometry and slope geometry, and it is controlling most of the parameters that we are usually normally introducing within the simulation. There is one more problem that very often we are working with 2.5, the topography, and this can be for example, extremely important for trapping effect, and sometimes we are not able really to simulate or to physically simulate this effect. Now it's possible to rely on a high-resolution topography, and so we are able sometimes to describe features at a submetric scale or sometimes a centimetric scale. So we have a very large amount of data, and we can use this data just to describe not only the large-scale topography, but both small-scale and up to the roughness at the local scale. One of the problems that I see in this case is that for most of the approaches that we are using, high-resolution topography is introducing a sort of redundancy in some of the parameters. So very often we introduce roughness in our model, but if the description of the model is already at an extremely high resolution, we are just simply introducing redundancy, and we are not able really to control exactly what is happening. And the same is occurring for restitution coefficient. So we are playing with restitution coefficient, but changing topography, we are changing the final result. So at that point, the restitution coefficient or some of the physical parameters that we are using, they are no more reliable. So they are not more, or they are scale, topography dependent. And so we should be careful about that. And so there is a strong sensitivity of the parameter to the topographic description that we are choosing. Okay, I'm just saying a few words about the code that Paolo Frattini yesterday said something about that. So we are developing through the year this code, and mainly in spare time, and with most of the energy that we can put on that. And it contains a list of possible features, and the input data are usually spatially distributed, like most of the software now in 3D modeling. And it can introduce, so it can consider a stochastic model, and it can work on high-resolution topography, any scale, down in a submeter scale. And actually we use that easily for lab experiments. And it can consider the impact on barriers, on rock sheds, and it can include block fragmentation, mentioning mainly, usually think of fragmentation in terms of high energy fragmentation with flying rocks and very low angle trajectories, and it can introduce impact forest and trees. Recently, in the last few years, we implemented also a user-friendly version. Okay, there is not. One of the problems of the modeling is calibration, and as explained from Paolo Frattini yesterday, it can be done in different ways. So we are just listing a few of them. The possibility to use the mean distance between the real block and the block in the model, or the mean value of all the summation, for example, of the distances between the real blocks and the results of the simulation, or the number of blocks passing close by to one of the, or to a buffer zone close to one of the real blocks, or arresting at a specific point within this area. And the same can be done along trajectories, so superimposing the trajectories, or looking at flying height, or velocity, energy, or the impact points along the profile. That is clearly a function of the resolution of the field data that we have available. In this case, we have simply some field tests, and we are comparing modeled trajectories with observed and recorded trajectories, and in this case we are comparing, for example, computed and measured velocity. Or we can, for example, implement the quality of our calibration just during the work. Yesterday there was a nice case study that simply was showing that they were designing a countermeasure, there was a major rockfall, and they calibrated the parameter on the event. And the same can be done, for example, when there is some cliff cleaning or trimming. And this is one of the cases, and especially we will see some of the in the next slides, we will see most of the application on this case study. Another way to look at calibration, for example, is to backtrack rockfalls. And for example, in this case, we can backtrack rockfalls starting from the arrest block position or from some building position, so we can fix the target, or the real block at the end of the trajectory, and then we can go back and fix or try to define exactly the possible source areas. This is important also because it's showing one of the main problems in 3D modeling, that is that you can have convergence or divergence of trajectories from very close by sources. The other problem that we have in calibration is why we are performing the calibration on which data set we are working on. So when one of the approaches is that calibration is just for a common rockfall that we are expecting, or for finding out the maximum runout event, or from multiple rockfall events. So one of the ideas is that if we have a source area or a series of source areas on this cliff, we will have the possibility to, for a block to arrest along the slope with a different probability. And this is the case with the maximum probability high along the cliff and the very low probability here. But we can have also the possibility to push the model, or usually it's what we do very often is that we have a major event, the block is reaching maybe a major road, and we want to design some countermeasure for that. So we are pushing the block and pushing the model to simulate all the trajectory that will reach this point. And this way we are raising the probability of reaching this specific point. So this will have a big consequence on the hazard and also on the final values of energy and velocity and height that we are computing. And the other possibility is just to consider a perfectly uniform distribution along the slopes, and that probably is what could be also in some cases geomorphologically compatible if we assume that there is a homogeneous way to grow for the tidal slope. What we can do for countermeasure design and optimization. Usually if we want to design for a countermeasure, we need to define the energy, as we said before, the velocity, the height, and the point of impact, and maybe the point of impact on the structure. And we want maybe to use different approaches for different kind of structures. At the same time, one of the objectives for most of the studies, yesterday there was some about this, is just to try to use a couple and not a decouple modeling between the rockfall events or the rockfall modeling and the impact against the structure. Again, this is the case study that I was showing before about the calibration of the model with the before and after trimming. There is a steep cliff, there is a main road, there are rock sheds, there are rockfall barrier at different positions along the slope, and these are just some of the results of the modeling, but it's not the main feature that we are looking at here. So what we can do, for example, is to, for linear targets, or almost linear targets, and for polygonal targets, we can use the results to compute, for example, the number of transit through each cell along, in this case are 20-meter long cells along the main road, or the number of transit through each specific building and structure, the maximum energy, the mean energy, the maximum height, the maximum velocity. So here we are in a certain way simplifying or using simplified parameters. We can do more. For example, we can put barriers along the upslope scarp of the road, or we can put a major fictitious barrier along the road, for example along the center line, and we can start getting all the data along this feature. So we are catching most of the parameters and the impact points. Here you see some clouds of impact points. Each color is in a class of energy. And here, for example, you have for each short box that we were seeing in the previous slides for the road, so each of these small polygons, we can extract the statistical distribution of the energy, of the velocity, of the height of flight, and so we can try to recognize safer or more dangerous areas or more hazardous areas. And we can suggest some clues about the design of these structures. So this is just a cloud of the hardest points of the blocks at the toe of the slope. And in this case, we are just classifying elements according to the number of impacts or the density of impacts. And we can choose, for example, for the type of impacts. It could be a flying impact against the roof of a building, or we can just study the rolling through the walls of the building, or a flying impact against the wall. And so we can again give more information about the possible energies at different specific points of the structure. One of the points we have seen that we can introduce very high detailed topography, and for some of the features that are commonly used as countermeasure is we need to introduce changes in the topography, and so this can be done with some tricks. And in this case, for example, we are simulating for the same case study the introduction of 3 different rock sheds with different length and with different characteristics. And together with the rock shed, you see there are some catch nets that have been placed along the slope. And we can simulate with a viscoplastic kernel, with a viscoplastic macroelement, we are able to describe the absorbing mattress that is being placed on the top of the rock shed. Another example of changing topography, introducing difference in topography for design of countermeasure. In this case is the actual condition along the slope, and this one is the design of the new slope with a benched slope and a catch ditch here, and a benched embankment and the final defended area. We are just along the lake here in the Lake of Como. And what we can do here is just to simulate from different sources the rockfalls, and for example start collecting data along this sort of sampling sheet or sampling window on the upslope side of the embankment along the ditch, and we can extract for that the spatially distributed percentile for supporting the design in terms of rotational energy, translational energy, velocity, height of impact, and again the same variable. So, and with the viscoplastic model that has been implemented, I think it was in 2006, we are able to extract or to derive from the data the penetration depth through the embankment. Another analysis that has been performed is the efficiency of the structure, and Federico was working on this, and in this case we have the same benched slope, the ditch, and we can compute the number of blocks that are easily entrapped in this ditch, and we will have in this way the total the efficiency of the upper part of the embankment. We can compute the total efficiency of the structure, and we can compute the residual capacity of the embankment, mainly considering the number of blocks that are arrested along the benches, and finally we can define the residual risk after the structure has been built. In this case, you see that there is a high residual risk as shown here in the plot. This is just a plot through 3 major areas, 1, 2, 3. Moving north to south, we have a relatively good efficiency of the structure in the middle part, but we have a bad efficiency here and here, mainly due to problem in the design, and also because here there was a change in property and between the ownership more than the property, and that was a major problem in the design. Okay, what we can do now with our model for hazard and risk assessment. We will pass through relatively quickly through this main 6 steps. There is a lot, I have to say that there is some uncertainty playing here, and we are making some maybe strong assumption, but definitely I think that there is a way to go through these 6 main steps to arrive to a quantitative hazard and rockfall risk assessment. So this is the same case studies as before. We are defining the source areas. We have a 1 by 1 meter cell DEM. We have some events that occur, very few of them, and so we were obliged to define on some historical data and literature data a cumulative frequency magnitude relationship. And so in this way we are defining the number of events that more or less can occur for a specific class of elements per year. Here you see the results for different scenarios. So we are considering, for example, a 0.01 cubic meter volume, and then for 0.1, 1 cubic meter, 10 cubic meter volumes, 100 cubic meter volume. So we have a different scenario, different model, and we can compute for each model the number of block transit through a specific cell with respect to the total simulated trajectory. And we can drag with us also one more information that if we have that, or if we assign it according to some specific design hypothesis, the probability of detachment from the source area. So in this way we are able to make one first step toward hazard assessment. And what it has been done here by Paolo was, for this simulation, we sampled the energy distribution at specific sites, at specific points for each specific cell. That could be or the 1 by 1 meter cell for the DM, or for larger polygon areas. In this case, what we observe is that with a reasonable number of simulated block, launched block, we see a log normal distribution of energy, and within each cell, and so we are able to make some assumption about the value of energy and the statistical distribution of energy within at a specific point in space. So if we have this and we can consider this, we can normalize our distribution, and we can have at this point the mean and the standard deviation for the distribution of energy at a specific cell, and from that and for each scenario we can compute the exceedance probability for a specific level of energy and a specific block. And at that point we can do that in terms of annual frequency, because we had the annual frequency of occurrence from the first step, and if we do that for all the scenarios, here for 6 scenarios, we can cumulate the total frequency, and so we will have a curve for a specific point on our slope that is described in terms of annual frequency and different level of energy. In this case, you see 55 cells. So each cell is represented by this curve, and each curve is representing the annual probability of exceedance for a specific cell level of energy. So at this point, if we sample along a line, we are able to sample a specific curve for a specific level of energy and assigning a specific return time. So that is quite useful, because from this hazard curve we are able to go to mapping hazard to real hazard maps. So we can generate maps for different scenarios. So in this case is an hazard map for 10 to the minus 6 annual exceedance probability, and then for 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. One more step to go through is just to define vulnerability to arrive to a reliable or more robust risk assessment. In this case, starting from a completely different kind of approach, but more or less taking for good that, and we can suggest different or some changes to this approach, but we were able to associate the probability of that according to a certain kinetic energy level. I would say that the most important thing is that we can define different curves, so don't look maybe exactly to the value. There were data about the vehicle exposure, and because there were some years of recordings along this road, and so in this way we were able to compute the vehicle exposure and to build up an FN curve, so in terms of annual probability of exceedance for expected number of deaths. And there are not so many standards available, and we can compare that, for example, with the GEO Hong Kong standard diagram, considering that the standard diagram has been designed for a specific length of the rocky cliff, so it should be adapted a little bit to the real condition that we are examining. In this case, we are shifting to the right a little bit the curve, and then we can plot again our annual probability of accident for expected number of deaths in the real condition, or after some changes and putting some countermeasure on the slope, and again by improving again the countermeasure. So we can, in this case, it's quite good because we are always, since the beginning, below or within or just at the limit with the alarm zone. But in this way we can sort of quantitatively assess the risk and try to design our countermeasure to fit as better as possible within this zone. Okay, so just to conclude, and I'm happy because I've been able to stay in time, that usually is not like that. So that is Rockfall analysis modeling imply a series of complex activities. Sometimes we are really making complex models and with a lot of consequences, and we should be careful about that. There is a strongly influence then on data, played by data and the models, and there is a strong redundancy that we are introducing very often in the models, but there is yet the possibility to arrive to a very robust and reliable definition of hazard and risk, and to support the design of countermeasure. And I think that at least is one step further toward a safe protection. Okay, thank you so much for your attention.